in. And so that's quite interesting to see that historical perspective. So instead of a physics lecture this afternoon, I'm going to be telling more of a story. I'm a storyteller. So let's get on with our story. This, by the way, is a nice view of the accelerator. SLAC stands for Stanford Linear Accelerator. And the linear accelerator is 3 kilometers long. You can see it from outer space. It's quite large. And it's nestled there in the hills around. All good stories start with a joke. And a typical physicist starts a joke by saying a quark, a lepton, and a boson walk into a bar. And that's the beginning of my joke, and we'll have to wait for the punchline till the end. And what I'm going to tell you about is a brief history of particles at SLAC. So this is my very crude timeline. And the very first elementary particles were discovered more than a century ago. The electron was discovered a long time ago. That's a very elementary particle. The photon was discovered. And then in between where SLAC starts in the 1960s and that over a century ago was a real mess of particles that we're going to have a look at. And what makes SLAC and Stanford outstanding is the discovery of something we now call the standard model that puts it all together. So that's what I'm going to try and explain to you today. And then the standard model culminates finally just a few years ago, 2012, when they confirmed the Higgs particle at CERN in Switzerland, another accelerator. So here we go. So SLAC itself, you saw it in the first slide. There's the 3 kilometer long LINAC. It's so long the freeway crosses over it. In the foreground are the experimental stations. This road that snakes along here is the road where SLAC is, and it's called Sand Hill Road, very famous road in the history of Silicon Valley. So Silicon Valley is an area all around Stanford, which I'll tell you a little bit about as well. So as I said on the previous slide, the last major discovery was the confirmation of the Higgs particle. And that happened during our 50th anniversary year, so we were rather pleased, because the discovery that led to the prediction of the Higgs particle all began at SLAC, and that's the story I'm going to tell you. And the very first experiments that were done in the 1960s at SLAC were what they call fixed targets. So the beam starts at this end, accelerates be careful, to what these large buildings here, they're called end stations. And in those end stations was a fixed target, and the beam would simply hit it, and there would be a detector on the other side of it measuring what came off. After the success of that, they said, well, we can get to much higher energies, that instead of making a fixed target, we'll do colliding beams. Because you know, if you're driving a car at 50 kilometers an hour and you run up the back of someone, it's bad. But if 2 cars collide at 50 kilometers an hour, it's catastrophe, right? And that's what we want in particle collisions. We want all the energy to go into the collision. So that was the next step, was to do colliding beam experiments. And so after the first discoveries at the end stations, colliding beams came. 1974 was a significant date, and it gets remembered at SLAC as the November Revolution in 1974, because that was the very thing that gave birth to what we now call the standard model. So let's proceed and describe what the standard model was. So before SLAC, there was a whole lot of subatomic particles being discovered at different accelerators around the world. And they had such wonderful names: kaons, muons, pions, and they had all kinds of subscripts and superscripts. And there were so many people who really didn't know what to do with them. They but they didn't know how they were organized. Then along comes SLAC. Well, before that, it was so bad, this zoo of particles. There's a famous magazine in New York called The New Yorker. And it showed one day that the poor cleaning lady had to clean up after the physicists every night and sweep up all the particles because there were so many. The fixed Higgs target experiment at SLAC was the first one that began to understand the structure and the interrelationship of all those particles. And on this side, this is the detector that was used in the experiment in one of those end stations that you saw in the photograph. So the target would have been here somewhere. And this is a very large machine, and you can see two people standing there. So that gives you an idea of the scale. So the beam is hitting a target here, the scattered particles come up to this detector here, and then this detector could move on these railroad tracks in a large circle all the way around the target and measure what we call scattered particles coming off. And what they discovered was that instead of just uniform scattering, there was a very distinct pattern. In other words, the electrons were hitting something not just coming off a proton, not just coming off a proton or a neutron, but something inside it, which we now call quarks. And the reason that we could see that was because the electron energy from the SLAC accelerator was so high. It was 20 GeV, giga-electron volts. And the significance of that is that the higher you go up in energy with your electron beam, you know there is a duality between particles and waves. So as you go up in energy, the wavelength of that equivalent wave gets shorter and shorter, which means you can probe smaller and smaller dimensions. So the early accelerator experiments had only probed something of this size here, and the neutrons and the protons, and then some of these others that were in the zoo before. What we saw now was that our electrons were not bouncing off this, but were bouncing off three constituents inside it, and that was the quarks. And now we could see that these particles were in fact related. They were just different combinations of quarks. So we were seeing the structure within the atom. We could see our high energy electron being able to resolve much smaller sizes, and with that we could see internal structure of what we thought were fundamental particles before. So with that success of that experiment, they said, well, let's go on, let's build more accelerators, go to higher energies and see even smaller particles. So the next machine to be built is our linear accelerator. There's the two end stations. It was this quite small machine, but it's a circular machine, a storage ring. It's called SPEAR, which stood for Stanford Positron Electron Accelerator Ring. And in that ring, there were two beams, positrons and electrons. Because they're oppositely charged, they would be traveling in opposite directions. And then there would be a detector on the ring, and that would detect where they collided. I'm going to show you the results of that, but it was so successful that they thought, well, if a small ring is good, then a bigger ring must be even better. So the next project that was built in the family of accelerators was the PEP ring. PEP stands for Positron Electron Project, not a very original name. But with a much larger ring, they could go to much higher energies. SPEAR was about 3 GeV, PEP was about 12 GeV, and they made more discoveries there. And then just to fill in the picture, they said, how do we go to even bigger energies? There was a project at CERN in Switzerland that said, okay, we're going to build a ring like PEP and make it 27 kilometers in circumference. And that was the LEP ring, which is now LHC, the Higgs particle was discovered. But the physicists at SLAC said, no, we have a better idea. We're going to do something called a linear collider. And the reason for that is because when particles move around in a ring, you're forcing them around corners the whole time. And a charged particle that is forced around a corner radiates energy. We call it synchrotron radiation. So all that work that you're putting into accelerating the particle gets lost. The harder you push it, the more you accelerate it, the more energy gets lost as synchrotron radiation. And it's a sort of non-winning game. So either you make the ring very big so that it doesn't get bent as much, or you go back to not bending them at all, just using a linear accelerator. So we accelerated positrons and electrons, and we took them around an arc, and we collided them here in this collider wall in the foreground. And that's where we discovered something called the Z particle, which I'll get to later. So that's an overview of all the different accelerators that we built. And then finally, we gave up on these and we built something called LCLS, but I'll get to that later. So I said that the quark model tidied up the idea of what all those subatomic particles do. The quarks came in two different types. One with a charge of plus 2/3 and one with a charge of minus 1/3. And things like protons and neutrons consisted of 3 of those. If you had 2 negative ones and 1 positive one, you would cancel out and get a neutral particle, or neutron. But if you had 2 of these positive ones and 1 of the negative ones, you would get something with a +1 charge, which is the proton. And then the other 2 fundamental particles were the electron neutrino, and then over here the photon, which was the charge carrier or force carrier. So that tidied things up, but it wasn't a theory of everything, and that's why it became important with the colliding beam machine to go to the next stage, which said there are more columns to be added to this table. So the November 1974 revolution was based on this storage ring called SPEAR. Here's the detector hall, so the beams are coming around, colliding here. And they discovered that at a particular energy there was a resonance, and they discovered the J-psi particle. And the significance of that, we'll see when we look at the table again. And I should mention that PEP was built after SPEAR. That was an even larger storage ring where they did quantum chromodynamics. They discovered things called the bottom quark and the gluon. And then the linear collider, which I mentioned, also looked at the Z particle. So let's move on and see how these things are arranged. And to try and understand why the standard model is significant, let's go back and look at the periodic table. Mendeleev proposed the periodic table, in other words, a way of organizing the elements back in 1906. And the significance of that is that he could put things in columns and rows, and when he did that, people immediately noticed back then that there were missing items on the table, and they went and looked for them, missing elements, and there were great discoveries in that time where they gradually filled in the whole periodic table. So that's why we wanted to do the same with particle physics, draw up the equivalent periodic table for particles. By the way, Mendeleev never got a Nobel Prize for that work, even though it revolutionized our understanding of the elements. So here's our periodic table for particles. The ones that we first discovered at the end station were in the first column rather, the up and the down quarks. The red ones were discovered at SPEAR, the charmed and the strange quark. People came up with unusual names for quarks. Why they had to call them up, down, charmed, strange, nobody really knows, but that's what they did. So the red ones, and then the blue here are the leptons. So we knew about the electron already, but the muon belonged to the same family, but it belonged in the second column, and the tau also is a lepton that belongs in the third column. So these two were discovered at SPEAR, and then the bottom quark and the gluon were discovered at the PEP ring, and then the top one was discovered at another laboratory that just happened to be Chicago Fermi Lab, but we don't talk about that much. And that got us 3 Nobel Prizes, so people were pretty happy about that. They tidied up all the force carriers. We knew about the photon, the carrier of the electric charge, the gluon that would carry the forces in the nucleon. the Z and the W particles, which carry the forces between the quarks, but none of them explained why particles have mass, and that was the Higgs boson, which finally filled in the table for us. So the Higgs was discovered at CERN. It was the last piece of the puzzle, and it confirmed a prediction from Peter Higgs. And that's Peter here, by the way. He predicted that there was a boson which was generated by a field to carry a force from one object to another. We know that the photon carries the force between charged particles, and as I mentioned, the W and the Z forces carry the weak forces, the blue one carries the strong one. But none of these particles predict why a particle has mass to begin with. And Higgs said, well, there could be another particle which would explain the mass, and I'm going to show you how he did it. First of all, I want you to know that bosons are named after Nathaniel Nathan Bose, an Indian physicist who was doing a mistake in his mathematics, but it was recognized by Einstein and turned out not to be a mistake, but a very significant piece of statistical physics that characterizes the behavior of bosons versus other particles. Let's go. Here we go. Okay, so this was going to be an animated thing that showed you how an electron, when it moves, generates an electric field, but we couldn't get it to work on my computer, so I'll skip over this one. The electric charge photons are all described beautifully by a piece of mathematics called Maxwell's equations. You're probably familiar with them. You should have studied them in your graduate studies. And the equations are so nice that Higgs said, can we use those same equations to predict a field that will generate the mass? And that's what he did. He used the same mechanism, the same mathematics to describe the interaction. We call it gauge fields. And he said it's possible to use that idea of a gauge field providing we do something called symmetry breaking. And he was able to predict that there would be a particle that would generate a field that would give other particles mass. And then, as we said, that was finally confirmed at the LHC. So that was now our complete standard model was summarized now in this table. So I don't know in Spanish culture if Tolkien literature is very popular. People know books like Lord of the Rings. Yeah. So there's a great quote in that. It says, "One ring to rule them all, one ring to find them." That's the LHC. One ring to bring them all in, and in the darkness bind them. So kind of describe the physics. So they only discovered the Higgs at CERN because the Large Hadron Collider is what we call a discovery machine, but it doesn't give us very fine measurements. What we need to do is make another accelerator, even bigger, that we call a Higgs factory, that would produce many of these particles in collisions. It could be a linear collider again, it could be a muon collider. There's a lot of proposals out there. All these machines would be extremely large and extremely expensive to build. And even though when you look at that aerial photo of the SLAP campus, it was a very large campus, there's still no way that that future machine could ever be built at Stanford. It would have to be built under the mountains in Switzerland, out in the middle of the desert somewhere, who knows, but it's not going to be built at SLAP itself. So that raised the question, what can we do at SLAP then? Well, I had this little slide in between. Is there any practical application for the Higgs particle? Can you think of any? No. But did Galileo have an application in mind when he showed that the sun was at the center of the solar system? Or is it the need to reveal the truth of the structure of the universe with any price? That's why we study physics. We can't imagine the world without electron and photon devices, right? You can't imagine life anymore with that. But it took us centuries after the discovery of the electron and photon to get where we are now with pocket devices like this. So we don't know what the practical innovation is here, but when you make the understanding, the applications come later. So what is SLAC doing in the meantime? This is now where our laboratory turned to photon science. What started as a minor investigation into synchrotron radiation, something that was considered a nuisance by high-energy physicists, right? In that sphere storage ring where the particles were going around and around. They could only reach 3 GeV because if they tried to go higher, all the energy would just disappear in synchrotron radiation. But it became increasingly useful to use that synchrotron radiation for other scientific research. So, as I said, the next generation of high-energy particle colliders won't fit on our campus, but the next generation of accelerator-driven, high-brightness X-ray sources does. So this is now part 2 of our story. Come on. There we go. So, a little history of the Stanford synchrotron radiation light source. These are some historical photos of when it was first built. The first synchrotron radiation users were just using the machine in parasitic mode. They literally made a hole in the side of the tunnel and a window on the beam pipe so that some of the synchrotron light would come out into a small hutch, and that's where the very first X-ray experiments was done. So that ring was the first multi-GeV storage ring based synchrotron radiation source in the world. And it was able to provide intense and stable radiation over a broad spectral range, including hard X-rays. And we're going to see in a moment how we can use those X-rays. So SPEAR then became fully dedicated to become the Stanford Synchrotron Radiation Laboratory in 1992. Now SSRL operates about 9 months of the year. It has around the ring about 30 different experimental stations, and it's available to users from universities, private industry, government labs, and foreign institutions. The applications of synchrotron radiation are chemistry, biology, medicine, environmental science, materials science, engineering, and applied physics. And there's over 1,500 scientists from institutions around the world visiting SSRL every year. So it's a big business. Now we get to the actual applications. Protein crystallography is probably the most notable application because it lets us untangle the structure of one of the most important life-giving molecules, proteins. That's important if you're trying to make drugs, if you're trying to understand diseases, you need to know the structure of the molecule. Protein crystallography uses X-rays, and because the wavelength of X-rays is very small, you can observe, you can image a molecule down at that level. And these are just some illustrations of different significant protein molecules that have been unraveled, if you like, at SPEAR. There's an interesting thing though in this title. It says protein X-ray, but crystallography. We know that proteins are not crystals. So what's that word doing up there? If we shine X-rays at just one protein molecule, we don't get enough light back, enough X-rays bouncing back into our detector in order to do our measurement. The way around that is to arrange the molecules in a nice even pattern, in a nice row, in other words, in a crystal, so that you can bounce the X-rays off a regular, organized structure of them. And that way, when you look at the diffraction pattern, you can understand the structure of all of them. It has some shortcomings. because it's difficult to make proteins into a crystalline structure. They're organic molecules. They don't want to be crystals. But you can persuade them to do that, and then you can reveal their structure. And now a little word about Stanford, Silicon Valley, and X-ray lasers. So Stanford research, the accelerator technology behind storage rings, and the discoveries at SLAC spurred the growth of Silicon Valley. Silicon Valley is just the name given to all the towns around the Stanford area. Many other regions now look to this as a growth model for economic and technological growth and development, because in Silicon Valley, surrounding our laboratory are all the famous companies like Apple, Google, Intel, you name them all, that's where they are. So, given that success, SLAC scientists began to dream of creating an even more powerful light source. We think, wow, storage rings are pretty cool, what can we do next? So people began to fantasize about making an X-ray laser. Right? Synchrotron radiation, although it's nicely directed, is still just normal, spontaneous radiation. It's not a laser, like what comes out of your laser. With an X-ray laser, we can make X-rays that are 10 to the 10th times brighter. 10 to the 10th is a number that is hard to imagine. It's not 10 times brighter, it's 10 with 10 zeros times brighter. And when you tell an experimentalist, I'm going to give you a flashlight, which is 10 to the 10th times brighter than the one you've been using, it's really challenging for them to think of what kind of experiment can I possibly do with this. And it took us a while when we made our proposal to build this laser to convince scientists how they might use that machine. But in the meantime, they have. So that gave birth to what we now call the Linear Coherent Light Source, or LCLS, and it's the world's first free electron laser, or FEL, for hard X-rays. And it uses the high energy electron beam from the SLAC LINAC that you saw in the photos in combination with a magnetic. And so this little cartoon sketch here gives you an idea. So this part represents the 3 kilometer long accelerator. The electron. Then at the end of the accelerator, they go through a magnetic undulator. These are just a series of dipoles which wiggle the electrons back and forth. And you know, every time you try and make an electron go around a curve, it radiates. But because you're now not just going around one curve, you're wiggling back and forth, the photons that you're generating will overlap with the electron bunch, and they will interact with the electron bunch. And something wonderful happens is that bunch of electrons that you sent in here now begins to get squeezed even more. And that micro bunching happens now at the same spacing or wavelength as the photons that you're generating. So in that micro bunching, you're getting a really high charge density, and now they will radiate even more brightly. So it becomes a collective avalanche effect, if you like. You start off generating spontaneous radiation at the beginning, but that radiation works on the electron bunch and makes it radiate even more brightly, and you get a sort of exponential growth in the brightness as you move along this undulator. So our undulator tunnel, it's about 100 meters long. These silver cylinders are holding the permanent magnets which do the undulator. It's quite a technological challenge because this has to be optically straight over 100 meters. That means within a micron. Because the photons, they're going to travel in a straight line. So our electrons must also travel exactly on that straight line. So we have to align everything perfectly. So that's the principle of operation. And we talked about the protein crystallography of the storage ring. How do we do it now if we have this phenomenally bright X-ray laser? So at a storage ring, we shine typically millions of X-ray photons onto this array, a crystal of say millions of molecules. And a few of those photons get scattered into our detector. And it's the number of photons reaching our detector that tells us how well we can do our experiment. But with an X-ray laser, we can shine a million photons on just one molecule, right? And now with a million photons hitting it, we can get enough light into our detector. We don't need to do a crystalline unit, right? We can look at one molecule all by itself. And that means we can even look at it in vitro, if you like, in its real environment before it's been modified through crystallography. So our ability to make that image depends only on how many diffracted photons reach that detector. But then you might be thinking to yourself, well, what happens to that molecule? What about the damage you do to it? You can't hit a molecule with billions of X-rays and expect nothing to happen. You'd be right. Within about 50 femtoseconds, 10 to the minus 15 seconds, that molecule blows completely apart. What happens is the X-rays go through the molecule, they take all the electrons out with them, and the molecule is left behind as just positively charged particles which repel each other, and so the thing blows up. So how can you take a picture of a molecule if you just blew it up? Well, let's be clever. Let's take the photo within the first femtosecond, because inertia will hold this molecule together for about 10 femtoseconds. Even though it blew apart in an incredibly short time, if we can take our snapshot, in other words, our flash picture with a camera, in a short time, like a femtosecond, then we get the picture of this molecule before the damage is done. So that was the clever solution. So what are some of the exciting applications you can do with that? Well, we saw all the applications to studying diseases, pharmaceuticals, new drugs and so on, but we want to study some of the most fundamental molecular reactions in nature. And what could be more fundamental than trying to understand photosynthesis? Photosynthesis takes photons from the sun, does something to the water molecules, allows them to combine with CO2 from the air, and store it then in another molecule, sugars, where the energy is stored, which plants and people can later use to burn and make energy. We haven't been able to reproduce that, but if we could understand photosynthesis, we might be able to copy it and make some very interesting energy sources. So the second part of having that really short pulse of light, that femtosecond burst of light, is that what if we take now multiple images of our molecules? We let our photosynthesis molecules get hit by some sunlight, and the changes are going to occur, right? And now we're going to take pictures with our X-rays at little intervals after that. And we will see the molecule change into all these other things. And it will be like a molecular movie, if you like. So that's what we've been doing with our experiments, not only getting the shape of the molecule, but understanding the pathways in the chemical reaction itself. So that's been one of the very exciting experiments in recent years, and it's still going on. A quick look at some of the other fun stuff we do. We don't only just do X-rays for proteins and molecules. We also study historical artifacts. This is an interesting one. This is Archaeopteryx. This is a famous fossil that was half dinosaur, half bird. It was a fossil that was of a dinosaur type creature, but it had feathers. And this showed the link between prehistoric creatures and modern day birds. So we used X-ray spectroscopy to actually study the structure of the feathers, show that they had the same molecular structure as feathers in present day birds, even to the extent of colours. So that was a really fun experiment to do. Another one of my good friends, is a study of the Archimedes palimpsest. Archimedes wrote some very famous documents and textbooks, but they wrote them on the skins of animals. And these skins were very valuable, so people tended to reuse books by scraping off the old ink and writing new stuff on top of it. So there was a book that had been supposedly written a few centuries ago in medieval times, and it was a biblical text, but someone noticed faint writing in the sides, and that faint writing under X-rays turned out to be the writing of Archimedes. So here they had a book supposedly only a couple of hundred years old, but now turned out to be thousands of years old with the writings of someone like Archimedes. And we could do that by tuning X-rays to specific wavelengths and looking at the contrast of the iron and the ink. So how is this relevant to other people then in other countries? SLAC has a history of supporting new international initiative, participation in collaborations and proposals for new initiatives. We host visiting scientists in engineering for training in accelerator and X-ray technology. We have a collaboration in building X-ray accelerators and detector systems. And we've even repurposed surplus equipment from SLAC so other people can build accelerators. These are some of the countries. Remember, SPEAR was the world's first storage ring to be used for synchrotron radiation. In the meantime, nearly every country and continent in the world has a synchrotron storage ring doing this kind of research. There's some notable exceptions, Africa, for example, and also Central America. Carlos and I have been thinking, how can we bring this science to Central America? Great science can also be done with small, innovative machines. So I want to tell you quickly about one of the machines that it would be possible to build in small countries on a smaller budget. Storage rings cost typically hundreds of millions of dollars, but what if you could build something that did almost the same size for about $1 million? And that's what we can do with ultra-fast electron diffraction. So that gun that we use to make the electrons at the beginning of our LINAC and make these really short bunches, femtosecond bunches I told you about, it will make electrons that are about an MeV in energy, but extremely short in time, and we just fire them at samples in our detector chamber, and we have a couple of detectors to look at the results. And what we look at are diffraction patterns. Remember, the study of the protein molecules was with X-ray diffraction. This one is now done with electron diffraction, but you can do very similar results. That's sort of bird's eye view of the beamline. I've got some of the numbers here to go with it, but we're kind of running out of time, so I'll skip through some of this. These are some of the components of the UED facility if you were to build something like this in your own lab. It uses lasers as well, so a lot of smaller labs are working with lasers, so it's a nice complementary thing. The other thing that can be done is to think about what can we do with small X-ray machines, what we call tabletop machines. And in the last few years, they've developed something called liquid metal jet X-ray machines, which produce very bright X-rays over a wide range of wavelengths, not as bright as a storage ring, but still bright enough to do some really interesting physics, do some imaging of structures, looking at thin films, since we were talking about that this afternoon, perovskites for photovoltaic cells. A lot of really interesting physics can be done there. The difference is, of course, the brightness of the source. An experiment that might take seconds or a few minutes at a storage ring would probably take 24 hours on a machine like this. But so what? You don't have to go to another country and apply for big time. You can just spend your weekend here and get your data instead. So that's the point I'm trying to make, is that X-ray science can also be done and started with small machines. So is the path forward for science and technology in emerging countries? We think we've shown that the history of SLAC and Stanford shows us that accelerators and photon science can be an ideal incubator for technological and scientific growth. We call it the Silicon Valley model. Building a synchrotron on a greenfield site has major impediments. It's really expensive and it takes a lot of expertise. So if you start with smaller projects like ultra-fast electron diffraction and tabletop X-ray machines, smaller countries like El Salvador, Central America, could make a significant start, because those small machines will serve to train students, it will attract researchers, and attract further investment from governments. So it could be the way into this sort of scientific world. And I think that was it. So I hope I didn't take too long.
Thank you very much, Patrick, for the nice and interesting talk, and for some ideas about how can we make research with small infrastructures, but we can get nice results. The example at the end was one of them. Now we can have a discussion. We can ask Patrick what we want. Dan,
yes.
Go ahead.
I have a question. First, I would like to thank for the amazing presentation. That's why it was very interesting. Is there another way to study the interior of the atoms, or just using one collider, for example?
So you want to look at the structure of the atoms.
Yeah.
So there are many experiments. So the purpose of SLAC was to study what the most elementary building blocks were, because the Greek word atom meant something that was indivisible. That's what the Greeks, they didn't know about protons and neutrons, but that's where that word came from. They just imagined, well, if you keep cutting something smaller and smaller, what's the smallest thing you can make? And they said that would be an atom, even though they didn't know it. So we said, well, what is really the fundamental particle? And that's what the Standard Model tries to show. Quarks, leptons, and you put them together are like Lego blocks, and you can build all the particles we know about, and those particles in turn will be the atoms that you saw in the periodic table. So that's what SLAC was trying to do. Other accelerators try and do nuclear physics. They will collide atom on atom, even heavy ions. That's what they did at GSI in Darmstadt, and Rick in Brookhaven. And they want to study how the nucleus, not the atom, not the protons and neutrons, but how the nucleus is held together, and why are there only, up to uranium in the periodic table? Why doesn't it keep going? That's what they're trying to understand with those accelerators. From those accelerators, you won't learn about elementary particles, because you smash nucleus and nucleus, like atom and atom. That's like taking many cars and smashing them head on. What you don't know when you look at the results, which car bumped into which other car, and how fast each individual car is going. So we call that equipartitioning of energy. So there are too many unknowns when you collide a lot of particles together. So if you want to do fundamental particle physics, you take single particles together, just electron-electron, or electron-positron, because they're indivisible. Yeah. So I hope that answers your question. Long answer.
Another question? Thank you.
In the Stanford, we are emerging economy. How the model of Stanford support this emerging economy?
So in the economy,
El Salvador, we need professors or just anti-capitalists. So I don't think something like that can happen here. But I was wondering about the proposal you were talking about, doing some kind of project, and that can come to that can enhance investments, and that can bring more people interested. What was specifically that idea?
So the Silicon Valley model has several components. One is that if you build a big project like an accelerator, you have a demand to build components that are sort of high-tech components. So industry will come along and say, hey, we want to build a magnet board, or we want to build a fly screen, or we want to do cameras, or things like that. So you become a very rich customer that will attract suppliers. That's one way. The other thing is Stanford was very forward-thinking, saying, okay, now there's other companies who are building accelerators. We will let them go up and start their own companies. So many Stanford professors are founders of companies like Google, and companies that build classrooms. Often they're accelerator components, but they have freedom to say, all right, you can be a researcher here, but you can also become rich if you want to.
Yeah, and I think you had an idea on one of those slides. What can we start here? What specifically was that?
I can complement a little bit that we have a project, a big project, together with Patrick and a lot of scientists around the world, in order to put a synchrotron in Central America or in the Great Caribbean, in the Great Caribbean. And then that's the reason why we are talking about that. Because Patrick said, hey, guys, we don't need to have a synchrotron that goes a couple of hundred, let's say 500 millimeters, for instance, not expensive one. Yeah. But we can put linear accelerator, like what Patrick showed here. It costs many, it's less than when you want to put a synchrotron. And that is the reason why Patrick said, hey, we can start with this kind of small machines. Yeah? And in this way, we train people, we attract investment, we attract the industry, we create jobs, etc., etc. We can get rich if we want, as a scientist or our engineer or whatever. And that's the reason why I wanted to complement, because we have a huge project about to have a light source in this region. Because as you saw, Patrick showed that we in this region we don't have a light source like a synchrotron. But yeah,
remember also the title of my talk was SLAC 60 years. That's how long it took. Right? So you start a project here, don't expect Silicon Valley to grow in 3 years, right? It took a long time. But if you don't start now, it'll take even longer.
Okay, but I have a couple more questions about that. Will someone in the private sector will be interested into investing into that? Is that gonna generate cheaper energy, or what is gonna be the
you will be studying things on your machine that are relevant to their industry. So think of an industry that might be growing, someone to some small government first, usually comes from the government, right? So the seed money. And then industry will say, hey, what do you do with $100,000 if we can do our experiments on your machine?
Have any kind of approach with the government?
Carlos's group has been talking with politicians and there's a consortium of people now.
This is a kind of project, but we can, for instance, we can ask for money from the government or other institutions like the European Union or the National Science Foundation, or for instance. Or that could be just for a start some project. No? But after that, we could develop a huge idea about more accelerators or grow like Stanford, for instance. Yeah? I mean, more accelerator, and then the companies will come and probably invest in this in kind of research because they are interested in some research, etc., etc. Yeah?
The first question they will want to solve is what would that be useful for?
Exactly. And we will show that because the application of this is not only particle physics. No? We have application in material science, in biology, in agriculture, in chemistry, in what else? Sorry? Medicine, health sciences, etc. And then there are a lot of research that we can do that together with the industry because they probably are interested in some products. For instance, that is the idea because when we talk about radiation sources like this, a lot of people think, oh, but why do we need to talk about quarks? Yeah? Yeah, we don't need quarks in order to be happy or in order to be, yeah? But we can do more than that. And for instance, in Spain or Italy, in Europe, in the United States, there are a lot of synchrotrons, and they make not only particle physics, they make applications for the industry, in order to solve problems, etc., etc. And that is what the people don't know right now. Yeah, many people. And that's the reason why we need talks like this, in order that the people are aware about, hey, synchrotron can be good for health sciences, for agriculture, for chemistry, for material science. Yeah.
And even cultural studies. That's why I showed you Archimedes' answer, right? Think of all the cultural things that get unearthed in Central America, and you can say, hey, we can study this with X-rays and tell you much more about them. Right? So it has a broad appeal to a community, not just the scientific applications.
Professor, thank you very much for your presentation. Now, question. Isabel, coming back in your presentation, we understand the standard model is the best way to interpret, to explain, measure. But there is a lot of things still missing, right? What is the main problem? What is missing so far?
Well, it doesn't explain gravity. Right? When I talk about those force carriers, the photons, the charged particles, and the other bosons, there was on that table in notice something called a graviton that no one's ever observed. But if we want to unify all the forces, which is what physics is trying to do, we have to try and explain the gravity. So that's still missing.
Okay, the second one is our country is working on the idea to install a nuclear power. What do you mean about it? This is a poor country. We don't have a lot of interest in investigation, in science. By this practice, nothing. So what do you mean? Because there is a political science, economical science, social
Right. Thank you very much. We have also here a question from high school students.
That's a good question. So, the energy efficiency scale as accelerator is very important. If I consider that, I talked about electrons having enormous energy, 20 GeV, but the energy in terms of joules, right, is charge, it's the amount of charge times that 20 GeV. And the charge of one electron is tiny. So multiply those two numbers together, and the amount of energy in one electron would not be enough to heat up your cup of tea. So, and you think about all the electricity that you're running in an accelerator, it's not a good way to make money.
One question? Yeah.
And so we need the signing of the protein. What technique is used to differentiate one protein from another protein?
Have you differentiated between different protein molecules?
And I don't know.
So the answer lies in diffraction. Yes. So it's simpler to start with normal crystal diffraction studies. So if you have regular rows of atoms in crystal, you bounce X-rays off them, and there is something called diagonal reflection, which is the impact. And if you look at the same layer underneath, that separation can be some multiple on the wavelength. And the X-rays will add constructively or destructively, depending on the separation. So what you do is you vary the angle of the missile X-rays, and then you look at ones bouncing off, and that pattern of light and dark, we call that a diffraction pattern. And measuring the diffraction pattern, you can reconstruct what was the spacing between different atoms. So that's in our regular thinking like crystal. But the same applies just to a single molecule. If you still get a diffraction pattern in a single molecule, when you look at the mathematics of how the diffraction pattern go on your factor through the instrument, it turns out it's just a Fourier transform. It's mathematics between the two. So our diffraction pattern will then go Fourier transform and go back through the original the delta. So that's all done now with massive computers, and now it's aided by AI. That's become very important in this company, because in the past it took a long time to figure out from the diffraction pattern what the molecule is. And now with supercomputers, neural networks, AI, it goes much faster.
More questions? Feel free to ask them.
It's something related with the accelerators, because I have read that right now we need to have like a large accelerator, like a ring, to accelerate particles more and more. Like, so one of the options that I have read is that we can, instead of build a ring, we can build a linear accelerator. So my question is if you can see a big difference between the build a ring and a linear accelerator, or it's like
So you notice that the first accelerator stack was linear. And even though we think circular accelerators are more efficient because it goes round and round, every time it goes round, you give another kick, it goes faster and faster. The energy loss to synchrotron radiation goes as the fourth power of the energy, right? So if I double the energy in the ring, the energy loss to synchrotron radiation goes as 2 to the 4. So it's hard, if you've got a ring this size, it's hard to get above the 7 range. But a linear accelerator, microscopic photography that lets you watch chemical reactions. And another reason to have a video.
I have a question. Patrick, here you have a lot of students, physics students, high school students, IB physics students here. Probably they are interested to know how can they go to Stanford, for instance, to an internship or to get a scholarship in order to stay there or to get training. You have seen that over there in a slide of Patrick today, Patrick's slides. You saw that you can go there. I mean, you don't have to be or live in California in order to use all the impressions that they have. I don't know if they are a special program for people from Latin America or something like that.
So this is something that I have to look into because I'm what they call the machine builder. So I help design and build the machines, accelerators that I've shown you. There's another group of scientists at SLAC, which we call the users. Right? They're the ones that come along and say, I have this project, and I know I'm good in this chamber and need to mention it. They don't care about the accelerator. They just say, hey Patrick, can you turn it on for us? They can buy it. That's all they care about. So usually the visiting scientists and ones from Latin America come as users. They come with a piece of equipment, and then they interact, and there's a whole community of people that help arrange to do that. And that's something I personally don't have a lot of experience with. But I can help find out and process information.
Exactly, that would be great because in this way, I mean, you can ask for big time, you know, big time means that you can go there to work together with technicians from SLAC or scientists from SLAC on make a collaboration in a scientific project. For instance, what Patrick said, we can have samples here. For instance, Alejandro's sample, he wants to know what kind of proteins they have in the sample and in human tissue. He can apply for a big time, work in a big time there, and probably you get funding to do that. Yeah? But this is, I mean, you have to have a nice project in order to go there. Okay, and there are also possibilities if you come, when you visit the website of SLAC, over there are internships, scholarship, visiting scientists, etc., etc. Or, yeah, you could apply for this kind of thing. Nobody knows you want, you get it, you funding or something like that. There is also different institutions where you can apply for this kind of states in the United States. For instance, Fulbright scholarships in order to make a mistake in Stanford. Okay? So there is another kind of program. Now it's a little bit limited because of the administration right now, especially for foreigners. Yeah, but there is some programs in order to go there. I mean, I have to say that yesterday when we were talking with Patrick, we discovered that a Salvadorian is working with Patrick.
Yes.
A Salvadorian I met. He was my classmate a lot of years ago.
So when your age,
Exactly, we didn't know. Like, if a Salvadorian is there, why not you? Yeah, exactly. He's called William. After a long time, I wrote after my talk to Patrick yesterday. hey, I know that you are afraid of Stanford, oh, you have to pay a lot of fee, a lot of money in order to go there, because it's a very expensive college, university. But there are another ways to go there. I mean, you don't have to pay a lot of money. Okay? Feel free to ask more questions if you want. If you want, you can ask in Spanish if you don't feel comfortable. In English, we could try to translate. Okay? El que acabo de decir que si alguno de ustedes no se siente confortable hablando inglés, pueden hacerlo en español, para que entienda algunas palabras, pero también le podemos traducir. ¿Ok? Así que no sientan, digamos, aprovechemos que no todos los días viene un científico de Stanford a la Universidad de Salvador, pero o al país. Entonces, sabe que tenemos uno allá, pero viene cada 20 años. Entonces, pregunten, siéntanse libres de preguntar lo que se les ocurra, aunque sea básico. Él empezó con el modelo estándar, ¿verdad? Eso es física en particular que muchos de ustedes han estudiado, o quizás no han estudiado todavía. Pregunten si quieren sobre el modelo, cuánto es un experto, tiene más de 25 años trabajando en Slack y además ha estado en muchos lugares del mundo trabajando, desde Australia, Alemania, etcétera, etcétera. También puedo preguntarle en alemán. Yesterday we were talking with Patrick in German. He speaks very good German. Very good, better than me probably. If you want
So I know you're from the German International School. There is a German International School in Silicon Valley. My wife is a teacher there. So I'm very pleased to be able to tell her that you came along to my course.
you can make also a change to Silicon Valley International School. Why not? Or other students like you. If you know a student that wanted to go there, please talk to Frau Braya, the coordinator of IB diploma program here, or they can arrange some kind of exchange to Silicon Valley. Not because you are finishing, but for younger students, for instance. Probably there is a possibility when you can visit the staff. For instance, you are there. This is another thing. Probably in Slack there are tools in order to show people interested in how it works. In many places around the world, and accelerators, you can go there as interested tourists, yeah, and get a tour in order to learn what they are doing. Okay? Questions? More questions?
Yeah,
Go.
in Stanford, are there some research involved in component studies? Are research involved in component studies? If you want to accelerate from it, what way is all
All atoms.
and all kinds of components?
We do electrons and
That
so there are other laboratories. So Fermi Lab in Chicago does protons. Brookhaven in New York does ions. And now they're building a new machine for electrons and nuclei.
I mean, in Stanford, are there all kinds of components that research?
Research about all Einstein condensates.
I'm sure there is, but I don't know. Because Stanford is a big university, it's a massive department, there's many different departments. And Slack is just one department. So there's physics, everything else, which is more than I ever knew.
But I think the challenge, the right challenge to get connections is professional there. Yeah, sometimes it works.
Yeah.
That works. Okay. More questions? if you here, for instance, we will put
So
from the very beginning with the title of your talk.
how do we make it full screen?